We're doing a video. I'm trying to make like all the demonstration stuff, a video of the stuff, so the next teacher will know what this stuff is. Right? So let's take a look at this. The first thing is we've got the this system. Now, if we say that this is height 0, if we ignore the fact that it's above the ground, we can say that this is 0 potential energy. Okay? And if we ignore the fact that it's going 900 miles an hour that way, why is it going 900 miles an hour that way? The Earth is rotating, right? Okay, so 900 miles that way, right? If we ignore that and we say, well, its velocity is 0, we could say that it has no kinetic energy, right? Why, by the way, do we launch our rockets to the east? And why do we launch them from Cape Canaveral? Why don't we launch them from up near the North Pole? Or how about why don't we launch them in northern Montana? Anybody know? It's not the coldness, although that would be a factor. Better weather maybe at Cape Canaveral. It's because we always launch it from as close to the equator, because the closer you are to the equator, the faster you're going. We always launch them to the east because they're already going 1,000 miles per hour, right? So if you launch a rocket to the west, and to be sure, I'm sure there's spy rockets that are orbiting the other way or something like that, right? Satellites. If you launch to the west, you have to reach an airspeed of 1,000 miles per hour, and then you're not technically moving. Right? You go west 1,000 miles per hour and you're just sitting still and the Earth is rotating under you, right? So we always launch stuff to the east. All right. So let's say that this is 0 energy. Now, if I do work on this, watch, I'm going to do work on this. I pushed on it, right? I exerted a force over a distance. This thing now has energy. What kind of energy does it have?
Potential energy.
It's got potential energy. Watch. The height has changed. It has changed. It has gained in height. What if I tried to figure out the energy with using force times distance? Why would that be difficult?
Because it isn't going directly.
It's not a straight line, so that's problematic, right? What about the force? Is the force changing as I push on it? Yeah, it's like a spring, but it's not exactly a spring. It's like mg sine theta or something like that, right? We would have to use calculus to figure out the work I did if we used force times distance. But I can tell you that it's the same as mgh. That's the work energy theorem. It has a potential energy equal to the amount of work I did on it, right? Okay. Now, let's imagine this is 10 joules of potential energy, okay? If I let it go, at the bottom, freeze frame, right? How many joules of kinetic does it have? 10 joules, right? Because it had 10 joules of potential there. At the bottom, it has 0 potential energy, so it must have 10 joules of kinetic, right? All right, let's do it again. What if I stop it right here where it has 2 joules of potential? How many joules of kinetic? 8. It's not going quite as fast, right? What if I stop it right here where it's got 7 joules of potential? It's got 3 joules of kinetic, right? We really couldn't solve this any other way. We could do the calculus of it and figure out what that changing force does to it, right? But that's complicated, right? Okay. And now, now it comes to the time where the teacher's got to put his life on the line. Okay? What I'm going to do is I'm going to put my head against the whiteboard here, okay? So that I can't chicken out. If this thing's coming for me and energy is not conserved, you're going to hear a gristly crunch and I'll just fall lifelessly on the ground. Yeah. And to further up the ante, I'm going to pre-engage the nose bones. I'm going to press this into the fleshy part of my nose until it encounters those bones that are in the nose, like this. Yeah? And I'm going to let go. Now, if energy is not conserved, death. Of course, equally, I suppose it could be life as well, right? Are we ready for this? Okay, here we go. Now, I feel like we should talk about friction too, though, right? So as it goes through the air, it's encountering the air, right? And that's going to slow it down. So I should be safe, right? Okay, here we go. And then also just like how you release it too, right? So when you release it, you don't want to push it, right? You don't want to give it a push because, here, I'll show you. Like if I push it, like if I give it a push, right? It's like, boom, right? All right, woo! All right. Okay, fine. I'm not afraid of no golden ball. Ladies and gentlemen, woo!